Hi, this is Dr. Mary Hansen, and this presentation is on entering data for and running a one-way analysis of variance and interpreting the output from that analysis. The research question that is asked in the one-way analysis of variance is a research question that compares more than two means. We worked with the independent samples t-test whose purpose was to compare two population means. It is possible that you would have more than two population means that need to be compared. In such cases, the analysis moves from the independent samples t-test to the one-way ANOVA. Data entry for the one-way analysis of variance is important, as it is for the different t-tests. Remember that each row in SPSS represents an individual. In our current study, we have individuals that have had one of three tutoring methods. Therefore, they have codes of 1, 2, or 3. Looking at the variable view, I have set up these codes so that 1 represents teacher tutoring, 2 peer tutoring, and 3 no tutoring. Next to each individual, their data score, in this case test score, is provided. Once you have the data entered, and again from this example you can see we have 5 people in the first tutoring group, 5 people in the second, and 5 people in the third, for a total of 15 people, 5 people in each group. In our data set, next to each group identification number, we have the actual data value. To run the one-way analysis of variance, you'll do Analyze, Compare Means, and One-Way ANOVA. Then we need to put the dependent variable, or the data that we'll be analyzing, in the dependent list, and the independent variable, which is defining our groups, as the factor. When running the analysis, you do want to click on the post hoc tests and then choose the appropriate post hoc procedure. Two common procedures are the Cheffe procedure and the Tukey procedure. You can see that SPSS provides a number of multiple comparison or post hoc tests, some when the equal variances can be assumed and some when they are not assumed. In a given problem, you would normally just run one of these procedures. In this particular analysis, I am running 2 of the more common procedures. Once you click on Continue, you can then click on the Options tab. One good idea is to obtain the basic descriptive statistics from SPSS. Some of this additional information is used when the assumptions of the one-way analysis of variance are not met. I definitely recommend that you obtain a means plot to get a visual display of the data that are being compared. Once you click on Continue and OK, a new output window will appear with the results from the one-way analysis of variance. Initially, you are provided with the descriptive statistics for the one-way analysis of variance, showing that the teacher tutoring group had a mean of 7, the peer tutoring a mean of 8, and the no tutoring group a mean of 3. We are then provided with the analysis of variance table. Again, the analysis of variance table shows very important relationships between quantities. We will be provided with the between groups sum of squares, which in this case is computed to be 70. The between groups degrees of freedom is 2, representing the number of groups minus 1. The mean square between groups is computed as the ratio of the sum of squares divided by the degrees of freedom, or 70 over 2, which gives us 35. Similarly, for the within group sum of squares, it's computed to be 36, the degrees of freedom 12, and the mean square for within groups is 36 divided by 12, or 3. As we look at the total sum of squares, you should see that it is the sum of the between group plus the within group sum of squares. Likewise, the degrees of freedom for the between groups plus the within groups equals the total degrees of freedom. The degrees of freedom in the complete study equal the total sample size of 15 minus 1. So our total degrees of freedom is going to be 14. When we look at the test statistic is an F value formed by the ratio of the mean square between divided by the mean square within. In this case, 35 divided by 3, or 11.667. The test statistic of F is utilized and could be compared to a critical value from the statistical table. However, when we run ANOVA in SPSS, normally we compare the p-value, or the significance, to alpha. In the one-way analysis of variance, recall that the null hypothesis is that all 3 population means are equal. The alternative is that at least one is different. From our p-value, we see that we would reject the null hypothesis, indicating that at least one of the group means is different from the others. Subsequent analysis can be run to show us which pairs of variables actually have significantly different means from each other. The Tukey procedure shows us that in the comparison of the teacher tutoring to the peer tutoring group, the mean difference is -1, which is not statistically significant, with a p-value of 0.64. The teacher tutoring, however, is significantly different from the no tutoring group. The mean difference is 4. You can see that it is starred. SPSS will provide an asterisk when the difference is statistically significant, and the p-value is 0.009, as expected, less than 0.05. So we compared the teacher tutoring to the peer tutoring group and saw that it was not significant, the teacher tutoring to the no tutoring group and saw that it was significant. The last comparison that we need to make to account for all the pairs of means is the comparison of the peer tutoring group to the no tutoring group, which has a difference of 5 points, which is statistically significant. You will notice that this SPSS output does repeat the information, as we've seen other times with the package. So there's no need to then again compare the peer tutoring to the no tutoring, or the peer tutoring to the teacher tutoring, since we saw that above. You can see the same p-value, the result is not statistically significant. Scrolling down the output, when you do run the Chef-A procedure, you will get this box that shows homogeneous subsets. Again, this output is another way of looking at the same output provided in the previous table. When you look at the homogeneous outputs box of output, any means that are contained in the same column are found to be not statistically significant from each other, while any means that are never in the same column are different from each other. Since in column 2, the 7 and the 8 are in the same column, that is going to indicate that there is no difference between the teacher and peer tutoring groups. However, since the no tutoring group, whose mean is 3, is not in the same column as either the teacher or the peer tutoring group, we can verify again our results with the same analysis that the no tutoring group is different from teacher tutoring, the no tutoring is different from peer tutoring, but again, because 7 and 8 are in the same column, the teacher tutoring is not different from the peer tutoring. The visual display from the means plot also shows you a graphic of these mean differences. What we found was that the ANOVA F test showed us that not all 3 means are different. The subsequent post hoc analysis showed us that the no tutoring group was significantly different than teacher, the no tutoring was significantly different than peer, but there was no difference, statistically speaking, between the teacher tutoring and the peer tutoring groups. One additional piece of information that you can obtain is by running Analyze, Compare Means, and the Means procedure. The Means procedure is run similarly, where we want to put the test score in the dependent variable list and the type of tutoring, our independent variable or factor, in the independent list. Clicking on the Options tab, we are going to ask SPSS to provide us the ANOVA table and ADA, a measure of effect size. Clicking on Continue and then OK, we can see that we get some information about the descriptive statistics and a repeat of the same ANOVA table that was obtained above. With this analysis, you also can get a measure of effect size in eta squared. In this case, it shows us that eta squared is 0.660. And again, eta squared is interpreted as a percent of explained variation. Again, this is Mary Hansen, and this presentation was on running a one-way analysis of variance in SPSS and interpreting the results from that analysis.